Hello everyone. Oh, wow, nice. Nice to see all these faces of varying familiarity. It's quite nice. Okay, so I'm here today in my software developer cosplay to show you this new project we've been working on. And this project is called Music Representing Corpus Virtual. So I just call it MRCV for short. And it's an artistic collaboration between myself, Lynette over here, Lynn, which is supposed to be, there we go, Lynn's there, and Sam, which is over there, there we go. And this is sort of the pre-concert workshop and like showcase code launch of this project. Okay, so I'll be just talking about it for a bit and explaining some of the motivations behind this project. So what we're introducing is a software repository, open source of course, a library for music generation, for procedural score and manuscript creation, for sound design and sonic exploration. And of course all these are like neural methods, open inverted commas. And so in a way I'm trying to say, don't be afraid to use neural networks, right? We always hear the term AI or machine learning and we go, oh, that's like not very, like it's not, we cannot immediately jump into it and get started. We have to like learn to write Python and learn to deal with pip and everything like that. So instead of worrying about all that, I've done it in a way where you can just click play and we're using neural networks the wrong way, right? So some ab initio attempts to try understanding this topic is we have some complicated object over here, and this complicated object might look dirty and hairy and like, we don't want to deal with it right now. So let's take a look from the more global and macroscopic view. So from the outside, right, macroscopic. And that way we can see the object in its entirety and appreciate it for what it is. And then also we can put in some inputs to the object. So in this case it'll be light, and then we can see an observable effect of the object. So in this case the shadow. Sorry if it's not a super accurate, shadow of the object. I try my best. But you can see either there's a shadow is there, right? So we can worry about the details later, all the hard stuff, right? I've labeled it there. Like we can, after we've done a few times of this observing the macroscopic view plus the observable effects, we can then start to say, oh, look, I see this loop over here and I see this sharp pointy bit over here. What does that mean? I don't know, but I see it. And then we can start to learn from there. So in a way, it's also a point of entry for people who want to be, to start learning these things, right? And we don't all have to go from, linear algebra and blah, 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 and then we get into it, right? So some small, simple concepts before we begin. The first being this idea of possible but not probable, right? It's not very likely, it's possible for someone, so a given person, to win the lottery on their first attempt, but it's probably not as likely going to happen, right? It's not likely going to win. They're not likely going to win the lottery on their first attempt. So it's possible but not probable. Secondly, I want to bring you this idea of like rapid prototyping and sort of setting up the boundaries for your creation without worrying about what it is that what exact steps we're going to take to get there, right? So the story I always say is, imagine yourself as a carpenter, and instead of growing the seed and getting the tree and watering the plant and then harvesting the wood and then bringing it to lumber mill and finally building your chair, why don't you just venture into the deep dark depths of some wet forest, preferably in summer, and find some decaying piece of wood, and from there you set the boundaries for your creation, right? You have this decaying piece of wood with spots here and there that it's not a perfect piece of wood. It's a piece of wood that you found, and then you're going to make your chair with that piece of wood. So that all comes in. And in that process, you're sort of getting in the ballpark of what you want. You're getting wood, you're not getting rocks, right? Maybe it's a bit too general an analogy, but you're getting wood, and then you're making the chair out of wood. So you're allowing yourself to be in the ballpark. So you're going to a forest, you're getting the wood. So another way of saying this is we have a dice that can give us many numbers, so like 1 to 6, but we only want one number of those. So we keep rolling the dice until we get our number, something like that, right? We can get in the ballpark of what we want. Another way of looking at this as well is informed guessing. So we don't know what we're going to get. We don't know how the neural network will work, but we can see from multiple attempts of putting in stuff and getting out stuff that can start to approach some understanding of it, right? And the last one being representations in high-dimensional space. The professionals call it latent space, right? Let's talk about that for a bit. I have a cool story about my chinchilla that I'll tell. So, this is my chinchilla, Pang Pang. Thank you, it's very cute, right? Yeah, so occasionally we'll let Pang Pang out into like a small play area, and she'll run about, and if I try to think about what she's gonna do at the next time step, my feeble brain cannot do it, right? I cannot immediately process she's gonna be there for next second. She's gonna go there for next second, right? Will she stay there at point A? So let me just point at point A, remain still. Will she move about to point B? Or will she kick off the wall and land at point C, as chinchillas are known for, and known as the parkour member of the mouse family, right? If you all know. So, if we think about that again, in a small area, if you have to model her movements, what will she choose next? A, B, or C? We don't know. But if I want to try and understand this, what steps can I take to then understanding this process? So, number one, I can think, okay, she has some sensory inputs, and these sensory inputs take in information from the surroundings. So like, we call them environment variables or whatever, features or whatever, right? So take in, if she sees a treat, she smells a treat, we put oats somewhere, those so on and so forth, right? Then we say there's interactions between the information gathered. So we say, oh, Pang Pang sees a treat, Pang Pang smells a treat, therefore there might be a treat there. And that's one possible interaction, right? And you can see that if you start compounding these interactions of what could be happening with her, you start to get this extremely vast landscape of high-dimension objects that can, you have two interactions, interacting with four interactions, interacting with three interactions, and if you keep scaling up forever and ever and ever, that will be a lot of parameters, right? So high-dimension representations. And then finally, all these high dimensions then collapse down into one single choice. She chooses to stay there, she chooses to go to point B, go to point C, right? So just to summarize that in a green flowchart for some reason, we have some environment variables, and the environment variables have, you can say she sees stuff, she smells stuff, sensory input X, imagination Y, whatever. And then she sees a food-like object, and so on and so forth, parameter. And then these parameters then have interactions again, and interactions again, and then finally we get to a single choice, right? So this is sort of how I would think about neural networks if I were approaching it from like a layman's perspective, right? So you can see that there are a number of columns where you can see like food, parameter, and we'll call that the layer width. So the more the layer width, the more parameters we take in. And the more interactions therein, amongst these parameter layers, we call them layer numbers. So like layer number 1, layer number 2. This is just for later, right? So, if we had enough of these latent, hidden, inner, high-dimensional parameters, we can model her choices, right? So formally, we like to say that exists for all x, which is the environment variable, some function x that gives you some input output y, which is the decision for all x, for all y, and there's some mapping m that will, as it approaches f, will give you the desired mapping of your choice. But which is what we just learned, right? We just learned that if we have enough of these understanding of hidden dimensions, we can approximate this function, the Pang Pang function, right? So, how do we then improve the accuracy of this model? Right? So how is this normally done? We can increase our parameters, right? We can say, okay, if we have understanding of more and more of these parameters or interactions, then we can start to get a better model, right? So bigger model size. Secondly, we can increase the number of observed instances of input and output, right? So if we stood there long enough and observed what Pang Pang says, or what Pang Pang does, sorry, she doesn't say much. What Pang Pang does, she can either stay still, she can either move there, she moves. And given what is happening at that point, if we record down every single thing, so it's 7:10. Our Muslim friends, if you want to break fast, please go ahead. There will be a time in between the end of this presentation and the concert beginning to eat your food as well. So if you brought food, that's also okay. But if you want to break fast, please go ahead. And thank you. Okay, so if we stood there for long enough and recorded each of our outputs, then of the inputs and outputs, we can then get a better understanding of the model, and therefore, it will train better, right? So, okay, Chris, I understand that if I have some bunch of observed inputs and I have some corresponding outputs, and I have a way to map these two things, we have Stable Diffusion, DALL-E, Midjourney. You give it some natural language, it gives you an image. Give me an image of a blue dog with a red nose, and it gives you the image, right? So natural language to image, input, output. Next, we have GPT models, right? Generative pre-trained transformers. So we have some words and sentences, and then it gives you some numbers to play with. So ChatGPT, sentiment analysis. I've done some stuff with GPT and dementia, so on and so forth. So how does that help me with audio, music, sound, score design, blah, 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 right? So before I get to that, I want to say, just for people who are like, this is so much code, I don't want to touch code. Everything is set up so that you can play around. You just press play and stuff happens already. So we've made it as introductory friendly as possible, right? Second, it's cool because whatever you feed in, as I'll demonstrate later, will not guarantee any idea of what you get out. Yeah? So, again, to introduce, MRCV is an easy-to-use code base. Everything is abstracted away, which means you just write pretty much English and you get to your objective. So it's a library of predefined functions for utilizing neural networks, the formal definition, right? So Neural Network 1, very inventive name, is our music generation network. And what this is we train this neural network, I'll get to it in a bit, on this Maestro dataset. And this Maestro dataset is a collection of 1,000+ MIDI files of piano performances, so actual humans recorded MIDI files. So you have time information, you have pitch information, you have velocity, which is the loudness information of a bunch of music from the common practice period. So I know the code is a bit small, but I'll walk you through the code without talking about the code too much. I'll try my best. So here we go. We give you a pre-configured model already, so the default model. We just say use neural net 1. So if you want to look at the code, it's available on GitHub. Use neural net 1 and you will get a neural net 1, right? And then you say, okay, I want to train on Handel and Mettner. And we've got a whole bunch of composers inside this list. So I think if you type F dot, it gives you Handel as well, because Handel has the middle name F dot. I'm joking. And so if you search for any composer combination you want here, you can put Bach, Mozart, Beethoven, blah, 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 and then it'll give you that combination of files into one big data set. And then you train your data set and you get outputs. So what can you control? You can control memory, which I'll get to in a bit. You can control composers. So in a way, are we trying to go for all these? Am I offering you this neural network so you can create more Bach music? No. I'm offering this to you so you can play with neural networks and you can explore what the different, limiting different sets of data will do to the output, right? So if I give it Handel and Mettner, and I say, okay, this gives me some output, which is the one you'll hear later, and then I give it just Mettner, just Handel. What's the difference there? Can we try to extrapolate something from the input-output mapping, right? And then lastly, you can get a parameter multiplier, which is I'll talk about it in a bit. I'll show you an example first. Well, finally you can hear some music. So I generated 100 notes of output from this neural network after I trained it on the Handel and Mettner set, which is about 100 files, I think. And this is what I got. So you can see, does it sound like Handel or Medtner? Not really, right? Right, I can, yeah. So, yes, so that was neural network 1. And so the idea, if you really want to think about it also, is we going to the point of trying to get to the ballpark that we want in the end. So if we want something like that, then it's a perfect area, and we can try and continuously generate more and more nodes, and then pick and choose what we want, and then craft it out from there. So you don't have to start from zero, right? You start from something and then you cut it down. So we have this model, and then the user is able to change the amount of memory the model has. What does that mean? Memory is how much the model can see into the past. So if we have 32 steps of memory, the model can see 31 steps into the past. And if we have one memory of one, the model cannot see any of its past inputs, right? So it's memory. We can change the amount of data the model is exposed to. So like I said just now, you can change to Handel and Medtner, or you can change to just Handel, or Handel and Bach, or Medtner and Bach, any of the composers in the list. And then you can change the amount of parameters the model has. So like the parameter multiplier, which is you increasing the parameters, which is what I talked about just now, right? With the if you have more parameters, you can approximate it better. But if you have less parameters, you get different results. So it's up to you to play with it. Caveat being that a bigger model requires more resources, so proceed with caution. Okay, so neural network 2. We have 4 of these in total, so hang on to your hats. Neural network 2 is a neural network that is trained on saxophone multiphonics, and we provide the saxophone multiphonics recorded by Sam. Sam, can you demonstrate some multiphonics, please? Choose your favorite one. Very nice. Thank you, Sam. Bravo. Let's keep it a bit casual. I think it's nice. So it's the idea that the neural network 2 is a method for sampler instrument generation. So we can generate 127 audio files with this neural network, and then we chunk them into a sample instrument, and then everything is written for you. So if you press go, you get a sampler instrument at the end of the day. So I'll show you that right now. So neural network 2, we train it on Sam's saxophone multiphonics recordings, and Sam patiently recorded all of the multiphonics, so it's very nice of him. I had a lot of fun working with it. So it's 228 audio files, and we ship you a pre-configured model structure. So you just have to press go. Again, you can change layer width, layer count. You can change the audio data, so it doesn't have to be saxophone audio. It can be clarinet multiphonics. I'm joking. It can be nature sound, it can be rain sound, it can be construction noise, it can be anything, right? And you can change other neural network parameters if you want. So if you want to change other stuff, you can, but defaults are fine. So we train with saxophone multiphonics. What do you think we'll get? Anybody willing to bet saxophone multiphonics? Ready? Okay, get ready. Hold on to your hats again. And to no one's surprise, we get hi-hats. Isn't that great? Of course, hearing like that is like, oh, okay, it's a hi-hat, right? Like, I can just get a hi-hat. Why do I need to do this? No, but it's a cool hi-hat, right? You can see it's like sort of modulating in space and everything like that. And we put it in context, right? You will never hear anybody ever once tell you these hi-hats were created by a neural network that was trained on saxophone multiphonics. That might not happen in the near future, right? So take that for what you want to do. Okay, so neural network 2. So again, what you put in, it doesn't determine what you're going to get out. So again, about having fun, about exploring, about trying different things and seeing if you can try to unpack something about neural networks for yourself, right? Also as an educational process, right? Also, I guess you can write a bit of code. You can have a guided tour of these new technologies and what they can do for us. It's not just like reserved for people that work in OpenAI or Google or Microsoft or whatever, right? It's open source already, but the entry point is not as clear as this, I guess, right? So I'm just trying to make that happen. What can you do? You can change the input data. So in this case, we can change from multiphonics to some other sounds.
You can change the model structure, like I said earlier. Of course, when you get the sound generated by the neural network, it doesn't just stop there, right? You can change it to however you want, like I showed you just now. I just added more reverb, added the compression, stuff goes on, everybody's happy, right? So continue what you normally do with your sound generation, sound design exploration. Okay, neural network 3. So this one we ship you the saxophone Ordinario dataset, which is Sam recording a whole bunch of stuff on saxophone, and that one has about 100 something files of audio, and this one is to create neural network audio plugins. So if you like audio plugins and you're lazy to write a whole bunch of juice code and C++ and CMake lists and everything like that, and you just want to grab a JSON, I'll show you later, but what you can do is we will export you a JSON file, and once you get the plugin, you can just drop the JSON file inside the plugin and you get your neural network in action, right? So again, I talk about the neural network a bit, so you can change the neural network structure, you can change the memory, you can try with different audio data and other neural network parameters if you want. So again, you look at the amount of code you have to write, it's about 5 lines of code compared to maybe, I think, 3,000 lines, right? I think, I'm just estimating here, of like Python and C++, just to get all this to happen, right? So again, I'll show you the effect of the plugin. So this is with it bypassed. So this is no neural network plugin yet. And that's a nice guitar tone, right? I guess people can agree with me. It's quite nice already, but what if we added our neural network? Do you think it will sound like saxophones? Anybody want to bet? No, right? Okay, let's see what it sounds like. And so you get this very cool harmonic-y distortion sound with a bit of room reverb inside. Who could have guessed that, right? We took a few hours, 1 hour to train this neural network. We dumped the JSON file inside this plugin that we have, and presto, we have a distortion effect now. And if you just try this with every other different kind of audio data, well, who knows what you can get? I think for once I recorded some bird sounds. I think is a Noiseville guys here. Oh. I tried this at Noiseville with some of their files. We got like a reverb out of a vocal track. So anything can happen here. I don't know what's going to happen, but I think the point is it allows you to try, right? Again, you don't know what's going to happen, so the neural network might catch on to details that you previously didn't pay attention to, right? So like I didn't hear the reverb and the distortion from the saxophone recordings, and so that's what happens. Next. Our last one is sort of audio instrument creation. So I was just say that it's neural wave tables based on Mel spectrogram. So let's unpack that a bit, right? So some preface to this is we have instead of using raw musical data like we've done in the past with MIDI, or I guess in this case audio files, any audio file can be written both in the time domain, which is the plot in time, and you can see my arbitrary y-axis logo. And so you can take a transform called a Fourier transform, for all those who want to know, and that will map it to frequency space. For those who have a not so good time with transforms and they're not your friend, think of it this way. I'll credit my friend Pete Kellogg on this. He's very nice. You can think of 2 water taps, right? The cold and hot water tap, those kinds. I'm sure you all know that, right? You can transform between the 2 spaces, right? Now we're in double tap space, and we can have percentage of hot water, percentage of cold water as degrees of rotation of each of the knobs, right? And now we can transform to our 1 tap but angle head space, that one where you can turn open and hot and cold is this way. So then we have degrees of rotation. Now we get vertical control of flow versus horizontal control of temperature, right? So they both get you some flow of water at some temperature, right? But this is a transform in 2 different spaces. One is in double tap space, one is in single tap space. That's the same thing with this. We have time domain and we have frequency domain. There's different spaces, right? So that's frequency domain. Next, wavetable synthesis. So for those who are not sort of synthesis guys, what we can do instead of generating the entire audio file is we can take 1 cycle of information. So we're leveraging the fact that music is a repetitive, there's a repeating nature of these harmonic sounds. So if you take a square wave here, for example,
they can see that the square wave repeats 3 times. And instead of generating the whole 1 second length of square wave, we can generate just 1 cycle, which is very, very small. And then we can just use that in our synthesizer, right? So again, in this case, you can see with sawtooth wave or with sine wave, the patterns are all the same. So when you generate your neural network, when you run the neural network, the file, you will automatically, it will procedurally generate, I guess the correct word is, this software instrument is for you, which it can be used in Decent Sampler. I'm sure some of you use Decent Sampler. And so what this does is, you can see okay, I have to say this again. The amount of code you write is minimal, right? It's 15 lines. I just want to keep repeating that. It's almost no code you write, okay? And then you get this Decent Sampler instrument, and you can then, it comes with attack, decay, release, sustain knob. So for those who really like that, I mean, I like that because it's nice. But you can use it in your DAW, right? So we can go from audio data that you train on neural networks, and instead of writing all that code, you can just have this and you can use it straight away. So it cuts the time for, I guess, production in this case. We can have very fast prototyping. So I'll show you the instrument. So this is trained on piano music. If you can see the word there, it says Kinderspiel. I will not comment on that. But it's trained on piano music. So this is the raw instrument. Doesn't sound like much, right? Sounds like, right? But I think I hear something inside, and I think personally I would do something to it if I were to get this from another synthesizer anyway. So I hear some wobbliness below the extremely high stuff, so let me just cut out the extremely high stuff and see what I get. And maybe on top of that, I'll put on some reverb as well. Let's play that again, sorry. Coolest 251 ever, right guys? Just joking. Okay, next, as part of MRCV, I want to introduce Generate, which is our procedural score generation part of it. And so it's some halfway point between Sibelius and Adobe Illustrator. So for those of you in the room who have done graphics scores before, it's very painful to do it in either of these programs, right? Or don't you wish you can just say, put this object in this part in space on the page, and then let it just procedurally do that for you for the rest of the objects, right? That'd be great, right? So why don't we do that? So we made this. I have to say though, the motivation behind this is, if you so the whole point is we want to link this up with the music generation part, so that when you generate the MIDI, it takes in the MIDI and gives you the score as well. So that way you have both the MIDI and the score, and then you can preview your score. So that's why we created this. And so, sure, you can use your hammer as a can opener, but can your hammer do this? So if you can't see that, I'll explain it to you. So what it is some small amount of code, again, I guess here is 10 lines, and then from there you get this directly generated for you, right? So this is just with all the default settings, and what really we created was the ability to procedurally generate the score as a bitmap. So it can handle procedural margin changes. So if you wanted to, let's say, every odd number page, I want smaller staff margins and I want bigger note hits, you could do that. And then you just click go and it does it for you, right? Now we can do input graphics at any coordinate, X or Y, give it an X, Y, and it'll put it there for you, so note hits, treble clef, blah, 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 blah. It gives you several helper functions for drawing lines and slurs and whatever. We also have some stochastic methods for pitch content elaboration, so like Markov models, I guess random is a stochastic method. And we have ways to insert text, so titles, composer names, first page indentations, blah, 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 blah. It's all there already. So just some examples of where we're at right now. I can just draw lines between the notes procedurally. I can also insert titles. I mean, font style is one thing, right? We can change the style anytime you want. Like font, we can change to our favorite font. We can use comic mono or whatever, right? So
In this case, it's just the default font I could find. And you can put the score title, you can put the composer name, you can put the instrument name, you can first page indent, you can change the staff size. You can see that here we're using the Markov model to generate the score already. So, next steps, and this is where you come in. If you are interested, feel free to talk to me later after the show, whenever you feel like, tomorrow, next year, about anything you might want to get started on with this, if you're interested. Not just with the score generation, but also with the audio stuff. If you feel like you want to contribute some documentation, some examples, some pre-trained, sorry, we'll get to that later. But just for January specifically, currently we are outputting a bitmap image, so it's not so sharp. It'd be nice if it was vector output. Also, there's no easy way of bringing in a MIDI file and converting that into a score. So it'd be nice if we could have that worked out. And then for other music-specific notations like triplets, dynamics, as in not the word MF and stuff like that, but like the crescendo and decrescendo, it's just a bit hard to do procedurally. So that takes a bit of braining, I guess, right? So yeah, if you want to contribute stuff for MRV CV, you can contribute not just a code, but if you have fun generating instruments and you want to generate instruments all the time, please share that with us. We'd be more than happy to put it on the repo and share it with everybody else. So one thing I heard about recently was all these very ultra big models, right, like Stable Diffusion, Midjourney, DALL-E, ChatGPT, GPT-2, I guess. They take so much power to train. I'm sure some of you know how much power there is. I heard anecdotally someone said GPT-2, the amount of power they took to train GPT-2 is enough for us to go from Earth to the Moon and back 8 times. So imagine how much liquid dinosaur we burn, right? So just for cool calculators. End of the day, yeah. So thank you all so much. I hope you all enjoy the show. Please give us some time to set up back to show configuration. But yeah, thank you to everybody who made this happen. Thank you, NAC. If I miss your name later because I have social anxiety or something, please, I can't thank everybody enough for this show, yeah? Thank you all so much. I hope you enjoy the show. So we'll give people some time to come back. But in the meantime, I'll just show you some things that we're doing for the show. So it's a whole system where Sam, you can see, is hooked up to some lights, and those lights on his arm, those are myocardiograms. Like, I guess they produce myocardiograms, like they're myosensors. So every time he flexes his muscle, we get the electrical signal of his muscle. And then you can see it on his left ear. His left ear. You can see the green light, and that's what's it called again? PPG, which is a pulse sensor. So every time his heart beats, you can see the intensity of the heartbeat, and we can see the rate of the heartbeat, I guess, right? And so we're taking all these signals, as well as you can see that box there, and that box also will give you some signals. So it's quite obvious later, but I won't spoil it for you. So we're taking these signals and we're feeding into a big system, and we're doing other stuff, and the system itself is composing some music as we go along as well. So everything is connected. Whatever I guess the players are also reacting to the music as well. So depending on what the system does, that's where the players will go, right? So yeah, I guess Lynette also you have some reactive system as well, right? So yeah, visuals are reactive as well. So everything is feeding everything else. So it's a big feedback network, and I hope to get a lot of fun out of that. So I think we start the show in a bit. Yeah. Okay. All right.
Sam and David over there. They're our great help. And then also the crew from the Arts House. Thank you so much. And anxiety kicking in already. Thank you NEC. Thank you RT Neuro for supporting this as well. So thank you NEC RT Neuro. Thank you Arts House. Thank you to all of you for coming. Thank you for coming. Yeah, if you have anybody, thank you. Oh, thank you the photographers. Thank you Dash. Thank you. Trevor, thank you Trevor. Yes. Yeah, I think that's it. Thank you everyone for coming to the show. Hope you enjoyed it very much. So the music, residency, oh yes. Let the Xuan and Auntie for helping out with front door as well. So sorry. Whew. That was hard. Thank you all. Oh yeah, I think the photo together in front. Yeah. With Lynn and